And so Earth Hour is organized by the Worldwide Fund for Nature, and it's just an opportunity to reflect back on your home planet. So Earth Hour itself is tonight from 8:30 to 9:30 p.m. In principle, the idea is to turn off our lights, and in theory it should make for better observing. Unfortunately, I believe it's going to be cloudy and rainy all night tonight. We will still have our domes open for some of our volunteers just to talk about how our telescopes work. But unfortunately, I don't think we'll actually be able to look through our telescopes. I think the forecast is calling for snow tonight. But as astronomers, we decided to use this Earth Hour event to really reflect back on our home planet. We really can't do astronomy without having our Earth to be here in the first place. And so tonight, for our Earth Hour event, we're doing a panel discussion on imagining our planet Earth as an exoplanet. What it would look like if we were to imagine observing it from a distance, if we were using our telescopes to stare at it from afar. What could we learn about our home planet as if it were a planet outside of our solar system? So we have some panelists. I'll ask them to introduce themselves in a moment. And then after this panel discussion, we also have a reception afterwards in the McLennan Physical Laboratory building. And so we'll have some of our volunteers leading everyone over, where we'll have snacks. Free food is always a nice incentive to stick around and try to chat with some astronomers. We also have fun things like 3D printed telescopes. We have some planetarium shows. We're handing out tickets. I'm not sure the status of the tickets, but I'll check before the end of the panel discussion. We also have an Oculus Rift. We've got some meteorites. Lots of fun things for people to check out with us afterwards. So we'll begin by introducing our panelists here. So we'll start.
Hi, can you hear me?
No.
Right now? What about now? Testing. I guess I'll try to speak louder if it works.
Check. Try this one.
Testing. It's a big difference. So my name is Manyin, M-A-N-Y-I-N. So I'm from the Department of Earth Sciences. I'm a PhD student there. I research on microbes under the seafloor, and I love the Earth because it's my beautiful home. Thank you.
Hi, my name is Paradise. I'm a fourth-year PhD student here in the Department of Astronomy and Astrophysics. And I study the climates of Earth-like exoplanets, planets when we start, what those planets look like, both physically and when we actually observe them. My favorite thing about the Earth is that it's the only planet in the entire universe that has wombats.
That you know of.
Hi, I'm Miranda Brennan. I'm a PhD candidate in the Department of Astronomy and Astrophysics here at UT. I also study exoplanets, but from an observational standpoint. So using telescopes and large data sets from space telescopes like Kepler to understand the population of planets and figure out what we can learn about them. I think my favorite thing about Earth is probably sunsets.
Hi, my name is Deepak Chandran. I'm a postdoctoral fellow in the Department of Physics at the University of Toronto. I'm in the Earth, Atmosphere and Planetary Physics group, and I'm a paleoclimatologist. So I use climate models and study paleo time periods in the Earth's past. So my favorite thing about Earth, it's a hard question, probably chicken.
Hello everyone, my name is Ben Pierce, and I'm a PhD student in astrophysics and astrobiology at McMaster University, just south here in Hamilton. My research is on the origin of life, focusing on the origin of the building blocks of life, whether they were delivered by meteorites or perhaps produced on the Earth in the Earth's atmosphere or in warm little ponds. And my favorite thing about the Earth is probably the ozone layer, because without it, we wouldn't be able to go outside very much because it would burn us.
to start things off, I'm just going to ask, what are exoplanets? When we think about our Earth as an exoplanet, what are exoplanets, and how do we observe them?
So, it's a bit loud. Exoplanets are just very basically planets that are not in our solar system. Exo means outside of. So, whenever we talk about an exoplanet that's not in our solar system, it's a planet elsewhere, on a different star. And we have a number of ways of observing them. We can look at how they block light as they pass in front of their star. We can look at how their star responds to the planet. You know that our sun affects the Earth in various ways. Gravity is a big one, but the planet also affects the star as well. It also exerts gravity on the star. As a result, the star will move a bit as the planet goes around the star, and we can observe that too. But those are all indirect ways of studying exoplanets and observing them. The more direct way is just directly observe them, take a picture. That's extremely difficult, and we can do it for almost none of them. But eventually they'll get better.
Does anyone else have anything they'd like to comment, or is that some are pretty good? Okay. So in terms of the existing surveys, or the ones that have already happened, missions that people have and scientists have done to search for exoplanets, can any of these have detected our Earth? And will upcoming telescopes or upcoming missions be able to observe planets like our Earth?
I can throw that one off. The answer is, could they have detected Earth? Sort of. If the odds of having detected an Earth are pretty small. And by Earth I mean a planet that's Earth-sized and takes a year to go around its star. The reason for that is to be sure that it's a planet, you have to see it multiple times. And when it takes a whole year to go around, you have to watch it for years and years and years, and we haven't been watching that long. But our telescopes are definitely able to see an Earth-sized planet block the light from the star. So we have discovered many Earth-sized planets, but ones that are at Earth distance are a little bit hard to find just for that reason.
I think another good point to mention is it really depends on what you consider Earth-like. So if you want something with the exact size and mass of the Earth that is at the exact same orbital period, that's going to be really hard to find. But if you're okay with looking for the same type of planet, but maybe around a different star, so it orbits a lot closer because that star is colder, so it's still in like the habitable zone, maybe you guys have heard of, then you could probably find a planet quite similar to the Earth that doesn't take a whole year to go around. So I think it really depends on how lenient you are with your definition of an Earth-like planet.
Okay. So when we're thinking about, we talked about, you mentioned the habitable zone. One of the big things for why we want to find Earth-like planets is to think about other planets have life outside of just the Earth and the solar system that we know about. And so one of the words that comes up a lot when people are talking about life on other planets, we'll talk about biosignatures. It's a huge buzzword. So what exactly are biosignatures?
I'm testing the microphone again. So, say if we are on the Earth, we can sample or observe life very easily, but we can't do that for exoplanets. Even if we can take samples, the living organisms may be too small or too scattered, so we may just miss them in the sample. So, but life interacts with the environment. So that way to do it is to measure what's in the environment. For example, as humans, we breathe in oxygen and we breathe out carbon dioxide. So we are constantly changing our surrounding environment. And that's why by measuring these chemical compositions, we can get a hint on whether there's life. They will make compositions of the environment different from a dead planet.
There's one more thing I'd like to add. There's a biosignature known as the red edge, which doesn't have to do with the gases in the atmosphere, but actually the vegetation that could be present on the surface of an exoplanet. So chlorophyll in all the vegetation on Earth, it reflects light that's in the near infrared, so just beyond the red part of the electromagnetic spectrum. So we see a bump if you look at the Earth in that region of the spectrum, and that's from this vegetation reflecting all that near infrared light. So that could be another potential biosignature that's it's not just a gas that would be present in the atmosphere.
Yeah, so maybe it's also worth adding that in addition to these examples of biosignatures, which are obviously natural examples of biosignatures, we would also look for more advanced signatures of biosignature. For example, by the fact that we are living beings, we have all these things that we just mentioned, but we also do modify our surrounding in many technological ways. We produce gases in the atmosphere that generally wouldn't be possible in a natural climate. So as an advanced technology, we have our own, as an advanced civilization, we have our own unique biosignature that might also be picked up, for example, if we're looking for that kind of life.
I think most generally you can think of a biosignature as is something that's not quite right with the planet. If you can't explain the planet using normal geology and physics, then maybe the thing you need to add to make it make sense is life of some kind.
Okay, so for Earth specifically, how does the presence of life, whether it's human or other life forms, what effects does that life have on the appearance of Earth and what it might look like in space? You commented on that, Edge. Are there other things really specifically that life, human or otherwise, do to really mark how our Earth looks from space?
Well, like I mentioned, we obviously have a very unique biosignature now because we are technologically advanced. We have, we are industrial civilization, so that could be one aspect to the thing. Thinking more, nothing else comes to my mind right now. I'll let you know. Yes, absolutely.
Speaking of being an advanced civilization, we have been emitting radio signals for like a century, and those kind of go pretty far because technically they're a form of light. So they travel at the speed of light and are going in all directions away from the Earth. So if aliens happen to be looking for signatures of life on Earth, they might detect the radio signals we've emitted and infer that something is on this planet to produce those. That being said, we've only been emitting those signals for like the last century or so, and they travel at the speed of light, so they can only have traveled so far in that amount of time. So the aliens would have to be within a specific distance to be able to detect us. Otherwise, the signals won't have reached them yet.
And adding to that, if they can see us from space, life definitely makes the Earth more colorful. For example, the rainforest, we see a huge patch of green color from the space. And they also have transpiration, so they release a lot of water into the atmosphere, which contributes to the formation of clouds on Earth. Other living things, for example, algae. If there's an algal bloom, then we can see them being red or brown in color. If we think about humans, then we have all the lights, even at night. And also think about the man-made coastlines and also man-made islands. For example, those in Dubai, those are what people or other organisms in space can see.
I'm actually really glad that you brought up algae because, as it turns out, that's actually maybe one of the more promising things that we can look for. When we think of the ocean's being blue or even bluish green, it's not actually what the ocean looks like, though. The ocean, there's nothing in it, it looks kind of flat. But if you add little living things into the water, it becomes this bright blue. So when you go to the Caribbean, you see these bright blue waters, it's because the things live in the water. We actually think that maybe you can see that if you're an exoplanet from Earth. If it's got a lot of this algae and these things living in the ocean would look bluish green more than it would otherwise. Maybe that's detectable.
and would that effect have been observable from space?
So I would imagine so. I mean, I'm not an expert in observation of planets from far away, but one of the promising techniques for understanding gaseous composition of other planets is to look at the absorption spectra of light that is passing through the atmosphere of an exoplanet, and then you're receiving it. That allows you to infer the properties of the atmosphere of the planet. And so if an alien civilization was in fact observing this for the past 100 years or 150 years, then they would see a significant continuous change in the composition of the atmosphere of Earth. And depending on how they interpret it, that would definitely be a reasonable signature of, that could be a signature of a civilization that is changing its atmosphere continuously. And as Miranda mentioned, there's also the effect of radio waves and the fact that we have been sending signals out. So if they have been listening for 100 years, then they might even catch some of those signals, and they might definitely find us, I guess.
I would actually argue that climate change may be our best indicator that we're here, because there's very few ways to make the planet look like it's changing the way it is. Our CO2 in the atmosphere has almost doubled in about a century or so, and there are very, very few ways to make the Earth do that on its own. One of the big ways we can make the CO2 spike very quickly is with volcanic eruptions, huge amounts of volcanoes. So maybe they would look at the amount of CO2 changing in the century and say, oh, they're going through cataclysmic volcanic eruptions. But with volcanoes, you also get other things like ash and dust and sulfur dioxide and other gases. And they wouldn't see those because we haven't been producing those in the way that volcanoes would. So they'd either have to conclude that we have very unusual volcanoes, or they'd have to conclude that something else is going on, and that might be life messing up the planet.
I got one more. I just thought of this. So this could be wrong, but the more satellites we put into orbit, the more that our planet will block out the light from our host star during a transit. So potentially, we could look at the further dipping of the light curve of the Earth, the more satellites we put in orbit. So that could be a sign of technological advancement. Perhaps.
Very, very good telescopes, but it's really possible.
Yeah, Adib's totally right. So that would be really hard, at least if the aliens were as advanced as we are. At the moment, we can definitely see like differences in what a planet looks like when it transits in front of its star. You could probably figure out that that transit doesn't look quite right. Maybe it has something else around it, a ring system of weird satellites. But in terms of what Deepak was talking about with the atmosphere of the planet, at the moment, we're not super great at figuring out the atmospheres of planets. So, like at the moment, all we can really do is look at these hot Jupiter planets, which have these enormous atmospheres, so they're pretty easy to figure out what their composition is. We haven't yet figured out how to get that down to the level where we could look at the atmosphere of a planet like Earth. So, we're a little ways away in terms of humans' advancement.
So we've been thinking a lot about sort of thinking a lot about life that really, for the most part, exists on the surface of the Earth. But are we limited just to seeing the presence of life at the surface? Could we see signatures of subsurface life looking at our Earth?
Definitely. And we don't have to infer nowadays. We can drill into the seafloor and we can find living cells there. So even 2 kilometers below the seafloor, there are still living cells. But those cells, because there is so little energy there, they're usually dormant, or their metabolic rate is really low to conserve energy. And the latest estimation is there is 10 to the power 29 cells under the seafloor. So that's 1 plus 29 zeros. And am I right that the latest estimation of the number of stars in the universe is 10 to the power 24? I think that's the latest number. Did I get it right? So there are more cells under the seafloor than there are stars in the universe. So the cells are everywhere on Earth.
I think it's worth pointing out that Earth didn't always have oxygen, right? That it took like 2 billion years to develop a large amount of oxygen. But when it showed up, everything was still living in the ocean. And I would count that as not really on the surface. So if you looked at Earth as it was 2 billion years ago, it was like the surface, like how
to that actually most of the life under the seafloor, they do not use oxygen even today. So oxygen is used up in very shallow part of the seafloor, and then life shift to rely on substrates like nitrate, manganese, iron, huge zone of sulfate, and then they even use carbon dioxide at the very bottom.
I did not know that. So thinking beyond our Earth, still thinking within our solar system, is there anywhere else other worlds that could have life past or even present today?
Yeah, that's a good question.
It's a big maybe. It's a big maybe, potentially.
We've identified a number of exoplanets that are roughly Earth-sized and that are roughly the right distance from their stars, especially
Let's
like
just start with still within our solar system.
in our solar system. You have places like Mars and Enceladus and Europa where you have some ingredients. You have liquid water, maybe sometimes, and you have various chemical things that things can eat. But we really have no idea what the ingredients for life actually are, or if they actually need those things. So at the moment, it is still a very, very open question.
Just to build on that, I would rank Mars at the top as the most likely, and then go Enceladus and Europa. And the reason for that is when you're thinking about the site for the emergence of life on Earth, if you're more prone to think of warm little ponds as being that location that first life emerged, well then you need a place where ponds could exist. And there's a lot of evidence that Mars was once a really wet planet. You have dried up shorelines and dried up riverbeds and teardrop-shaped islands that are carved by ancient river streams. So you would undoubtedly had warm little ponds on Mars as well, which means that if there was a second genesis of life on Mars, that life could have perhaps evolved to the changing Martian climate and stayed in places where there was liquid water, places like the South Pole region where they've recently discovered a subglacial lake that's 20 kilometers wide. So this would be a place that I think would be most likely place that life as we know it could exist. If you go to places like Enceladus and Europa, now you're no longer looking at warm little pond environments of emergence of life, but these hydrothermal vent environments. On the ocean floor, on Earth, we have these fissures where a lot of hydrothermal fluids escape, and there's a lot of heat and energy. And the Cassini space probe, which was orbiting around Saturn, went to Enceladus and it found molecular hydrogen coming out of these plumes on Europa. And the main way to get molecular hydrogen is to have water-rock interaction, which means that there could be hydrothermal vents under the ocean floor on Enceladus. So if you're more prone to think of that as the location for the emergence of life, maybe you could put Enceladus above Mars. And then when it comes to Europa, there's no evidence for any hydrothermal activity, so we wouldn't really understand that origin of life. Not to say that there's no life there, but we wouldn't be able to connect to it as much because on Earth, it's really just these two competing hypotheses for the site of the emergence of life, warm little ponds for hydrothermal vents.
I think that's an important point that we should really emphasize is that when we're talking about life in this panel, we're talking about life mostly like us, life like we understand on Earth, because that's what we know. But you could certainly make an argument that maybe there's life in the clouds of Jupiter, and it's just nothing like what we know, but we wouldn't recognize it if we saw it, which is why we're focusing on life like that we know on Earth.
Okay, so at this point, we'll open things up to our audience for questions. So we have a couple of microphones in the two aisles over here. And so we'll just ask if you'd like to get up. We have a couple here, and we'll just take as many questions for the next little while. We'll see how things go.
Hello.
Hello.
You were talking about radio waves going out into the universe from Earth over the past 100 years. I really love the opening of the movie Contact, where they're way out there. How far do you know? Have they been out of the solar system? How far away are they? And have they gone light years away? Do you know approximately?
What's the first transmission? Does anyone know?
if it's roughly a century ago, then it would have traveled 100 light years, since light travels that distance in 1 year, which I think, I did the math earlier, works out to roughly 950 trillion kilometers. So that sounds really far, but in terms of astronomical scales, it's nothing. So not super far. To put that in context, the closest star is about 4 light years away. So we've gone about 25 times past that.
I think I was wondering if it was, they got no other star or not. So definitely.
Yeah, for sure.
And definitely past Vega, which is relevant for contact.
To add on to that last point, just looking at my math, but I think if you go 200 light years at that point, the volume is big enough that you're enclosing many thousands of stars. So our radio signals have traveled far enough that there are potentially thousands of planets that would receive them.
Okay, so we have, we also have a roaming mic. This one's definitely working now, right?
Yes, yes. So on your list of Mars, Enceladus, Europa, the moon Titan, does that come anywhere on that list, or is that way down there?
It would be next in the list, but I wouldn't put it on the list just because the main liquid on Titan is methane. And it's a non-polar molecule. And when you have a non-polar molecule, it's really hard to dissolve things like organics, something that could actually create a biomolecule, such as a protein, or something that could actually have some sort of function. With water, it's polar, it has a negative and a positive side. Ions of water can bond really easily to it and dissolve, so it's really the perfect solvent for having life. There may be other solvents that could do this, but methane wouldn't be one. Ammonia could be possibly one. So on maybe some exo world, there could be some ammonia solvent space flight. But yeah, I wouldn't put Titan on for life as we know it for sure, and that's mainly the reason. Cool.
Okay, so we'll take a question on this side.
Hello. Okay. So I was wondering, when you're studying exoplanets, and especially when you're looking at some sort of images of light that's coming from that direction, I assume that's the case. How do you think about the fact that you're kind of you are looking into sort of the past, and that's not what's going on there now, because the light takes so long to come here to our planet. So how do you think about what's really going on there now versus kind of what happened when that light was originated?
Oh, yeah, I have the example. That's a good question. So all of the exoplanets that we know of are in our own galaxy. We haven't been able to detect any further away than that. They're all pretty close. So while they are certainly like maybe, I don't know, a few hundred light years away, which means it's like a few hundred years in the past, that's not a huge amount of time in astronomical scales. So correct me if I'm wrong, but I feel like it's not something often taken into account because, I mean, we're not looking for signs of life for most of the things we do. So the changes we're going to see are not going to happen on that short of a time scale. They're going to happen over millions and millions of years, which we can't see anyway. So, yeah.
I think the exception is that if we find signs of intelligent life, and then there will become a question, okay, we got a signal from 200 years ago. Are they still around, or did they blow themselves up? And there would be no way to know because we sent a response and we wouldn't hear back for double that time. And in that case, do we really care? I mean, we learn what we can, and we'll all be dead by the time we respond anyways.
Okay, so we have a question here. And also note, so for anyone that's just difficult to get to the two mics that we have in the stands, we also have a rowing mic, so you can put your hand up and our wonderful volunteer will make her way over to find you. Okay, we'll take your question, thanks.
So the answer to this question is probably a more subjective answer, but we've talked a lot about planets that exhibit Earth-like qualities. Is there anything else out there that we should be excited exoplanets that are really exciting for you as you guys see it? I'm just curious what you think.
Can I go first? Oh gosh, yes. So many. Earth is actually pretty unusual. The most common kind of exoplanet we call a super-Earth, something that's larger than Earth but still less than a few Earth radii. And even if you don't go so big that it becomes like gaseous, like with a big gas envelope, just keep like still a solid surface with water and Earth-like atmosphere, even those planets are just so different from Earth. The dynamics are totally different, the surface conditions are different, their interiors, how volcanoes and matter work is probably very different. And then a lot of these planets we've discovered are around small stars that are close in, and they actually do what the moon does, where the moon, the same side always faces the Earth. You only ever see the same side of the moon. These planets do the same thing. The same side always faces a star. And that is also just a radically different climate regime. And the conditions are totally different, the climate is totally different. And we just barely scratched the surface of what those are like. I think that is just very, very exciting.
I also think hot Jupiter planets are like the coolest thing ever. They are the same roughly size as Jupiter, but they have orbital periods that are like a day. So they whip around their star really fast, which means they are really, really hot, and some of them are like hot enough to boil metal, which is just insane. And they have like crazy inflated envelopes because they're so hot, and we have no example of that in our own solar system. So I think the discovery of that type of planet was pretty cool because we had no idea that those giant planets could exist so close to their stars.
I've got one as well. This hasn't been discovered yet, but the prospect is definitely there. There's a lot of Jupiters that have been discovered that are 10 times the mass of Jupiter. And the reason this is exciting is because our Jupiter has things that are the size of our moon orbiting around them. But something 10 times the mass of Jupiter could have something the size of the Earth orbiting around them. So you could get an Earth-like planet that's heated, instead of from the star, but from tidal heating, from the flexing of the insides of this Earth-like moon, creating enough energy for life to perhaps emerge on an exomoon. So I think that prospect's really exciting, and there are definitely people looking for exomoons.
So it's my childhood dream of a forest moon and indoor with little Ewoks, potentially true.
Oh yeah.
Okay, we have a question up here.
I was wondering, why is Europa on the list?
Why is it on the list?
Yeah, because you mentioned that it doesn't have hydrothermal vents like Enceladus does.
Yeah, it's third on the list. The only reason it's on the list at all is because liquid water has been confirmed underneath the surface. It's just thought that it may be solid ice, liquid water, solid ice, and then a rocky core. So no hydrothermal vents. You could imagine life emerging from some sort of freezing and thawing cycle where organics can be cycled down from the ice crust into the ocean. There could be something there. I wouldn't say there's a highly likelihood that we'll find life on Europa or underneath the crust, but if we do, then that's all the more exciting. I still think we should look, because if we find it, then we have to explain how did that occur.
I have a follow-up question.
Sure.
So why haven't we explored whether there's life on Europa?
So it's in the works. There's the Europa Clipper mission, which is set, it's a reconnaissance orbiter, and it's set to take off in 2023. And because it's a reconnaissance orbiter, it's got a lot of instrumentation. It's got some things that can detect biomolecules that may be coming out of the plumes of Europa, but it won't actually make its way into the ocean. It's not a submarine, it's not a lander, but you could potentially find out a lot from flying through these plumes and seeing if there's any organics, seeing if there's something that once was living and then UV got to it and it kind of destroyed it a little bit. But some of those relics are still in that sample. So that's in the future. That's coming. And then after that, if they find enough interesting things, then perhaps NASA will find the follow-up missions actually get a lander that will melt through that crust and send in a submarine to swim around and see what they find.
Which I think gets to the real reason, which is because if you have more taxpayer money going towards space missions, we can do more Europa missions.
anyone have any insight into the future James Webb Space Telescope and its ability to perhaps analyze the spectrum of the atmosphere of exoplanets for molecular biomarkers such as O2 or O3?
I am not an expert on the James Webb, but it does sound like it's going to be a huge improvement on our ability to look at the atmospheres of exoplanets, like hot Jupiters and maybe even smaller ones, and should definitely be able to look at different molecules and tell us more about their composition. So it should be like the next step up if it ever gets launched.
To add on that, the thing that James Webb is going to be very, very good at is what's called transmission spectroscopy, where you watch how light passes through the atmosphere as it kind of blocks the star. James Webb is going to get amazing at that. The problem with that is it only really probes the top of the atmosphere, so you're limited then to things that you can observe on the top of the atmosphere, which water's not one of them. But oxygen you definitely good.
One more thing, in addition to transmission spectroscopy, you can also do emission spectroscopy, which is where you actually look at the emission from the planet itself. But to do that, it is really difficult because the planets aren't very bright, and the stars are, which is problematic because they're really close to the planet. So in order to do this emission spectroscopy, you have to have a really bright planet and look at the right wavelengths where it's going to be bright. So that is a little harder to do compared to transmission spectroscopy, but still really informative because it can tell you a lot more information than just the light traveling through the planet's atmosphere from the star. It's the light from the planet itself. So.
Question up here.
Hi, I actually have a follow-up question for Ben. So,
Hi, Sarah.
hi Ben. Follow up to your exomoons comment. If you have life forming on exomoons, or potentially having exomoons hit it by just tidally or tidal heating, how do you think that will impact life, given that life as we know it requires radiation from the star to exist?
Question. Sarah's a McMaster alumni, so we go with that. I suppose that if the Jupiter is close enough to the Sun, that when the exomoon Earth-like world orbits around Jupiter, it can get some solar radiation on its backside. Maybe that could be favorable. The way that light is beneficial for us here is that it's really good at making biomolecules in the atmosphere. Things like hydrogen cyanide, things that seem actually really dangerous to us, are actually really good for prebiotic chemistry, stuff that could make the first life on Earth. So if you don't have things like ultraviolet radiation, then that might be a problem. However, galactic cosmic rays can play the same role as ultraviolet radiation, and if you're orbiting around Jupiter, it's got a really powerful magnetic field, and it's going to be taking all the solar, wind, and all the cosmic rays that are all these basically charged particles traveling really high velocities, and they're going to direct them right onto the planet. Those are going to go through the atmosphere, and they're going to do this kind of really favorable chemistry. I would say that there's a possibility there that the same process is just a different kind of energy source.
Question up here.
Hello. Do you guys get a say in where the telescopes sort of point, and how do you guys sort of choose where to sort of point them, and what kind of star system would you like them pointed next?
We totally get a say. It requires writing really detailed observation proposals, which are annoying, but you can choose a target and say you want to look at this particular planet, so you apply for time to observe on whatever telescope you want. You can even apply for time on the James Webb Space Telescope if it suits you. But it's very competitive, and they allocate time to people in different countries, so that everyone gets a fair chance to do these observations. It's up to the scientists what you want to study.
So from my geological perspective, I'm particularly interested in planets. with plate tectonics. Because like Ben mentioned, hydrothermal vents, plate tectonics enable the vents. So it has a steep chemical gradient, and a lot of reactions can happen within a small place. And many different types of organisms can form a symbiotic relation there. And also, plate tectonics kind of enable the accumulation of oxygen on Earth. Because even though their photosynthetic life made oxygen on Earth, if oxygen is directly in contact with, say, hydrocarbons, then the oxygen is used to degrade the hydrocarbon. No extra oxygen will accumulate in the atmosphere. But if plate tectonics enable quick burial of the hydrocarbons, cut them off from reaction from oxygen, then the oxygen can accumulate in the atmosphere. That's why many processes important for life depends on plate tectonics. That's why from a geological perspective, I'm really interested in those matters as well.
Just to add one more thing, I think it's really important to consider what kind of science question you want to answer with your observations, and not only what telescope you choose to use, but the instrument attached to that telescope is far more important, I think, because the specifics of the instrument can do so much more than just a bunch of mirrors, which is essentially what the telescope is. So that's also really important to consider in addition to the science question you're trying to answer.
Okay, we have a question up here.
Hi. So this calls for a bit of speculation, but I'm wondering if any of you can comment on the distinction between finding life versus finding intelligent life. And I'm just thinking that, so, you know, as these new missions go forward over the next 10, 20 years, we might find, I don't know, dozens if we're lucky of planets with life, or maybe hundreds, or maybe thousands, but we might have all of that and still not find the slightest sign of intelligent life. But, I mean, I'm guessing there's a huge question mark over that, because we don't know how much of a fluke it was or not to get intelligent life here on Earth. So can anyone comment? I appreciate this is a tricky question, but can anyone comment on that?
This is kind of a rephrasing of what's called the Fermi paradox, which is if life is common, and if there's life everywhere out there because there's millions and billions of planets, then where is everyone? And so if we find many, many planets that have life, and none of them have intelligent life that we can see, then what's going on? Are we a fluke or what? There are a number of different ways to resolve that, so I wouldn't be particularly concerned if we didn't find intelligent life. And my sort of personal conclusion, if we had to work the scenario, was, well, maybe we're just not recognizing it, or it's not making itself known. A good example for me is these planets that have the same side always facing the sun, that are tidally locked. It's likely that the day side is the side that can support life. But any life that emerges there, the sun never sets, the sky never changes, they never see the stars. So if there's intelligent life that emerges there, they may not really have that kind of, they may not be prompted to think about the world beyond theirs, they may not send signals out into space, they may not go into space, because it might never occur to them that there's a space to go explore if they never see it.
For anyone who missed that, Miranda just said that's so sad.
I might just add that it's also a matter of strong probability. Like, I mean, life has existed on Earth for over 3.5 billion years, or 4 billion years, being trying to get it. So if you're just an alien just looking at Earth for that long period of time, the chance that you find intelligent life is minuscule compared to time period that life has existed. So, I mean, we will never be able to sample enough planets, at least in the near future, to get a good measure of that statistic. So, but it's looking at that, I think, it's most likely that whatever life we find, we'll just be looking at a planet at a time period where life, intelligent life just hasn't evolved. But it might, probability-wise, it just hasn't. So, I think it's probably just probability that's really an indicator of faith there.
I also want to mention that intelligent life has existed on our planet for much longer than it was detectable. And when we think about detecting intelligent life on other worlds, we're thinking about a species that's technologically capable of creating some sort of techno-signature, whether that be, you know, a mega superstructure around the star that can collect energy directly from the star, or just radio waves or some sort of infrared communication waves. Homo neanderthalis or orca whales. You know, they were undoubtedly on our planet for a while, and you know, as far as any intelligent aliens knew, looking at our planet, they could find life based on the biosignatures in the atmosphere, but they wouldn't be able to distinguish that those beings on that planet were in fact intelligent. We're in fact, you know, multicellular. So there's that distinguishment made. I think that's important. Is when we think about intelligent life, it's also that you're technologically capable, and that's really the main focus of looking for life, intelligent life in other worlds with SETI.
Hi, just as an individual question is partly asking this. We hear about astrobiology as a subject matter commonly in science, so to speak. If you can just enlighten people like me, like what is happening in astrobiology and what is the extent, and apart from the obvious limitations, where does it stand at the moment?
So I can answer this question. So at McMaster, we have one of the only astrobiology programs in the country, and the study of astrobiology is really the focus of the study of the origin, the evolution, and the distribution of life in the universe. Right now, we only know of life in one place, so we're really focusing most of our energy on how life emerged on our planet, but there's also looking for life on other worlds, focusing both in the solar system on these other worlds we mentioned before, Mars, Europa and Enceladus, and then on exoplanets as well. And you know, we are still working through the problem of how life emerged on our planet. You know, I still go to conferences where there's fierce debates, debating just that location, just whether it was a pond or whether it was the hydrothermal vent. And people are doing research actively to try and narrow that down. I do research in the warm little pond camp, and I'm prone to think that that's a more likely place for it to occur. But there's many people who do research in hydrothermal vents and are coming up with a lot of great research as well. So to tell you where we stand, you know, there's still many gaps in the story for the origin of life on Earth, and we're working through it. But I actually am very optimistic and think this is a problem that will be solved in my scientific lifetime. So I think in the next 30, 40 years, we'll have a strong idea of the pathway for the emergence of life on Earth from a formation of the Earth and the moon forming impact, from the solidification of the magma ocean, the creating the first oceans, first ponds, to creating the first organics, and those organics coming together to form the first biopolymers, which then could replicate and create the first genetic molecule that could replicate itself and therefore meet the most basic definition of life, which is just to make imperfect copies of yourself. So I think that's definitely solvable in our lifetime, and we're working on it.
Okay, so just keeping in mind the time, the last two audience members who are setting up will have their last two questions. So we'll start with you.
Okay, most of the biosignatures that have been discussed are basically transmission spectra through the atmosphere of these planets. But isn't there a potential biosignature that could come from geology? On Earth, geology is heavily driven by life. Life processes create the white beach sands of the Caribbean, and they create limestone, and they create oil shales, and actually create the oils that actually lubricate some of the motions of tectonics. So I'm thinking, looking at that, thinking, wouldn't there be some sort of transmission spectra that could be related to rock formations that might actually tell you that there at least has been life in the past on a body? And thinking along that line, is the red color of Mars potentially a biosignature?
So speaking as a non-expert, I would immediately think that what you're saying, the various aspects of biosignatures, like the limestone, the shale, etc. Those are genuinely important aspects of biosignature. The question is, how do you detect them?
Yeah.
Like how they have to somehow interact with, let's say, a medium that through which information is conveyed to us here. And generally, the absorption and emission spectra are the most common methods of transmission of signals that came from other planets that we're familiar presence of shale and limestone, but as far as I know, I'm not entirely sure of what those interactions could be. So it becomes an issue of how these surface features are interacting with the atmosphere through which starlight is passing them to them. And yeah, I want to know, but I think that's a pretty hard problem. What about?
So I can actually comment on that now. So when you talk about how like these white beaches, they're white because they're from a limestone and these crushed corals.
Well, it's a silica, actually. It's processed through the...
But it's a biosignature because it's formed by life, and you can tell it because you can see it, right? You can see that this is this white color. That's a biosignature, and you can see it. The reason you can see it is because light is hitting it. So a lot of our research has gone into transmission spectra, light passing through the atmosphere and continuing on. But a new area of research that's going to start opening up as we build new and better telescopes is actually, well, what if you look at light that hits the planet and bounces off, reflected light? Then you can directly measure the color of the surface because you're seeing the surface. And that would be quite a bit easier then to say, oh, well, it has this change in color that is probably due to life. That's quite a bit harder than transmission spectroscopy, which is why we can't really do it yet. But within the next 20, 30 years, that will probably be the best bet for discovering that kind of thing. And then the challenge will be, is this uniquely a biosignature? Or are there other forms of geology that we don't know about, that, because they don't happen on Earth, that could instead produce the same color? And that's sort of the challenge there, is how do you know if this color is life, or if this color is just weird geology?
The Mars aspect, right? We know on Earth that our oxygen in the atmosphere is produced by life. And that begs the question, is Mars red because they had life, the oxygen went in the atmosphere, and then it all rusted onto the surface? And would that count as a biosignature of a dead planet that once had life?
Maybe. I don't think we really know. We only have one data point for Mars, and we can't see what happened to Mars in the past. So maybe some future rovers can answer that question. But at the moment, that's not the question.
If you expose iron to water, it's going to rust. So I think that there's too much of a alternate explanation for that, other than life. So it wouldn't be conclusive, but it would be interesting to find that elsewhere.
I can comment a bit more on that about rock records. I don't know whether they can be studied with spectra, but I can comment on what we can learn from the rock records. So the first thing, color, it may not tell us directly whether there's life, but it's more about telling us the environment. Like if it's red, it means it's an oxidized form of iron, not a reduced form. So it tells us if life exists, what type of environment they're existing. And the second thing is isotope. So it's like carbon. Life needs carbon, and there are lighter carbons and heavier carbons. And life usually prefers the lighter form. So it's like the lighter form is candies, and the heavier form are like carrots. Imagine there's a kid in a room with the same numbers of candies and same numbers of carrots. After one day, we go back to the room. The kid has probably eaten some candies and some carrots, but probably more candies than the carrots. So there will be more carrots left in the room than the candies. And that's why if we can measure the ratio of these different types of carbons, it can actually be a biosignature of life. And rocks are really good because they're what's left after billions and billions of years. So they are strong evidence for us to study what has happened on that planet. But I'm not sure about how much the spectra can do to study rocks.
You know, I'm actually going to make a prediction. We're not quite at the point where we can measure isotope fractions in spectra, but that's in theory possible. And I'm going to predict that in, say, maybe 60, 70 years, that's going to be the #1 way that we identify biosignatures, isotope fractions. It's very, very difficult. We can't do it right now, but it is something people have been talking about sort of in the hush conversations at conferences like Off to the Side.
Can I just add one last thing from my perspective, which a bit of an outsider is, so I really need to connect to it. So speaking of carbon isotopes, what Manning was really alluding to, just to reiterate, is that life prefers a certain kind of carbon isotope. And so if you have organic dead material, the composition of lighter to heavier isotope of carbon is pretty different from, say, just any other pool. And in Earth, speaking of just biosignatures. I wanted to, as you mentioned, one of the biosignatures of human existence is climate change and the presence of CO2. And you can really say that it's fossil fuel CO2 because the isotope composition of the carbon dioxide in the air mimics the isotope composition of dead plants and material. So it's because we are digging up fossil fuels, and these fossil fuels have that isotope composition of living forms. That isotope composition is reflected in the atmosphere, and in essence, for us, it's one of the most strongest evidences that the presence of CO2 in the air is man-made because we're digging up the fossil fuels, not some other thing. Otherwise, it will have a different isotopic composition.
Okay, we'll take our final question of the evening.
Sorry, this is really dumb. Have we fired off like a rocket or anything to any of these kind of could be habitable planets with just like amoebas and diseases and algae and stuff just to see what happens? Or, and if yes, what happened? And if not, why not?
So, first, could you clarify, are you asking, can we send a rocket to contaminate these planets?
Yeah, man. It's like, fucking like.
So, we could do that. We haven't, well, we might have done it. We hope not. Oh, gosh. One of the big science questions is, has life emerged independently? And if we go and stick microbes there, they might survive. That would be very, very interesting for a number of reasons. But we would never be able to answer the question of, did it emerge there on its own? So NASA has what they call a planetary protection officer. It sounds like an awesome job title. But that person's job is to make sure that all the agencies are complying with like very, very stringent protocols to make sure that nothing gets off into space. How effective that is, there's microbes in the air, and so it's not entirely clear if we can really effectively prevent them from getting on our spacecraft. But we try not to believe the bodies are trying to study.
And it's just because like you want to be able to observe it, or because?
Yeah, if you'd like to answer the question of if we find life there, is it from there or did we bring it? And that would be a really easy question to answer.
Thank you.
Just to add to that, I mean, we generally, to avoid contaminating areas where life may or may not exist, doesn't just extend to the other planets. Even on Earth, for example, when you find very pristine situations that have been isolated from the rest of the Earth for a very long time, there's generally very strong procedures that one has to follow before you reach or sample that kind of environment, because there's a strong consensus that you just don't pollute something. For example, we have these subglacial lakes under the Antarctic ice sheet that have been isolated from the rest of the Earth's atmosphere for over 700,000 years. And there's probably life there, but we can't easily probe it, and we can't easily test it because you might end up just contaminating it. And so you can't just go in there with all guns blazing. You have to sort of be careful there.
One last comment. We've been unintentionally contaminating a lot of these worlds. Every time an asteroid impacts the surface with enough energy, it'll send ejecta into space, and that's why there's some Martian meteorites on the Earth that we've analyzed and have matched the spectra and found, yes, this is a meteorite that came from Mars to Earth on its own. We didn't bring this back. This wasn't a sample return. So it's very easy to imagine the reverse happening, where an asteroid impact on Earth, maybe the one that extincted the dinosaurs 65 million years ago, would have ejected a lot of material into space, and that would have made its way over to Mars, carrying the microbes that could survive that with it. So it's just a thought, that we kind of have been contaminating these places.
I actually read earlier today that we think that several tons of rocks actually made it to Titan from that dinosaur impactor. And that some of them would have probably carried microbes. So maybe we should just go and prep microbes because we've already done it. So.
Yeah, exactly.
Why not? Let's have some little people.
Okay, well, this is bringing to our panel discussion portion of our evening Q&A. So before we thank our panelists, have as incentive for providing us with feedback.